So what is mean shift? Well, mean shift can be somehow seen as a kind of density-based methods, but it's a kind of thing in between partitioning methods and density-based methods. So let's have a look at that. And it's quite a popular method, by the way, currently. Even it's quite young, I would say. 10, 20 years ago. Anyway. So let's see. The idea here is that it uses an algorithm from the 70s. You're from the 70s and I'm a 90s, whatever. Anyway, so it uses an algorithm from the 70s, which is called iterative mode search. And the idea here is find the modes in point density, meaning the area, the objects, the whatever, that represents the highest point density somehow. That is somehow the mode in that context. And the algorithm is quite simple. We select a window size epsilon, and a start position m, and then we calculate the mean of all points inside this window m. So the window could be a sphere or just a kind of rectangular window, no problem, and the size, so the size of the window length, so to say, in all dimensions is epsilon, or the radius of this sphere is epsilon. So let's consider it a sphere. So we take the starting point m, so and we take a sphere centered at m with radius epsilon. So that is the window. And then we calculate the mean of all the points inside that window. That need not necessarily be m, right? Because the points may be scattered somewhere in this sphere. So we just compute the mean of these points in the sphere. And then we shift the window to that position. And then, so let's assume that the window originally was here, and now we shift it to be centered now at the mean of the points inside this sphere. Now we shift it and again compute the mean of all the points now in this window. So we shift it again a little bit, so it's going to be somewhere shifted until nothing changes anymore. So you can even prove that there will be a convergence where the window is not shifted anymore. And that is the mode of highest point density, so to say. So here is an example. We maybe start with the m, the mode here, and calculate the window with size epsilon, which is just a sphere of radius epsilon here. All these spheres have radius epsilon here, and that is the first starting point, the first potential mode. And then we calculate the mean of all the points in this thing here, which is probably somewhere here. So we move the sphere, the mode, which is the center of the sphere, we move it to this mean here. And then we again calculate the mean of the points which are in this sphere now, which is this, and this, and this probably moves the sphere down here, and so on and so on and so on. And somewhere there is some kind of convergence, meaning that the center, the mode, gets stable. The mode is not changing. The mean of the points inside this sphere is not changing anymore, and then we stop, obviously. So that is mode search, and if we do that for maybe all possible points, then we probably get a good idea where the modes in the data sets are actually. And that's the idea of the mean shift algorithm. And you see here it's not as old as agriculture, but more or less 20 years. So the idea is pretty simple. It applies this iterative mode search for each data point, not for just one point or one artificial starting point, but we use each data point as the starting point for this algorithm, actually, for this M here. And we do that, and then we see, okay, some of the points converge actually to the same mode, which is called in that case Bazin of attraction. So all these points are somehow attracted by a common mode. And those points that have from which the iterative mode search converges to the same mode are actually grouped together into one cluster. Quite clever. Well, of course. And you see here that those are So this is the data set, a two-dimensional data set, and the color coding obviously is what the mean shift algorithm actually gets. Yeah? And you see that, well, it's a kind of density-based clustering algorithm with some kind of fuzziness at the borders here. Yeah. But it's also kind of partitioning algorithm in that case. But, and that's the good point, let's see the discussion before we look at the extensions, see the discussions. The clusters can have actually arbitrary shape and size, and there's no restriction to convex shapes, even though it seems to be the case here a little bit, but that's not the case in the general form. Yeah? And also the number of the clusters are now determined automatically, because we're just grouping the points that have the same attraction of Bazin of attraction. Yeah? It's also robust to outliers, because those guys, those outliers will have a different mode, a different Bazin of attraction. So and maybe they don't share this their Bazin of attraction with anything else. So they are marked as outliers, as singleton clusters, as outliers. Easy. It's easy to implement and easy to parallelize, which is sometimes good for big data, of course. Has just one single parameter, the window size, which could be a little bit nasty, of course, but well, you can play a little bit with that, no problem. Yeah. The downside is that the complexity is quite high. The runtime complexity is quite high, so we need for the windowing a range query, a neighborhood epsilon range query, which takes typically O of n for each point, meaning we are already in a quadratic effort, and then we have to do that a couple of times. In order especially to group the modes, which gives us, if we have T clusters, which is not known before, the T is not known before, of course, so if we have T clusters, we get T times n squared. N squared is just because we have to do the windowing for all the points, and one windowing for one point is already linear, so n times n, of course. So relatively high complexity, which is of course not so nice, and meaning also we cannot play too much with the parameter. That's the downside. And one of the extensions try actually to tackle that problem. That is the second one here, the binning. So that is kind of extension in order to make the mean shift a little bit more scalable. So the idea is that we quantize the data points to a grid. So we just partition the data in grid cells, somehow arbitrary, and then apply only the iterative mode seeking once per bin, meaning that we aggregate the points in a bin to just one mode, so to say. So there is only one mode per bin, and then we group those binning bins that have the same Bazin of attraction again. So we just work on a kind of coarser granular representation by applying a grid first. And that obviously reduces the whole effort to a quadratic effort in the number of grid cells that we have. Which again is only sensible if we apply that on a lower dimensional data set, but that's a different story. And then another extension which is quite common. Well, of course, we could, when we complete the means here, we could do a lot of mathy and messy and whatever things in order to somehow bias the method towards or reduce bias of noise points and stuff like that, and also accommodate different assumptions about the data. So in that case, we can use just the weighted mean, and we can use different weights for the points in the windows. For example, by using some kernel here, some kernel function. So instead of just computing the normal mean, we can compute a kind of weighted mean. And you can formulate that as a kind of kernel function, or by means of kernel function, which means that you don't have to transfer or transform the data into this kernel space here. So you can apply different kernels here, which is sometimes a little bit more handy to program and also then to calculate actually. Yeah? So here you can think of different things. For example, try to weight things that are a little bit closer to the center of the data, or to the center of the starting point of the center of the sphere, a little bit higher, for example, so that you may get a little bit less sensitive to noise. Yeah? The mean is sensitive to noise. If the sphere is small, no problem about it. If the sphere is very large, so the epsilon is very large, then you may have a couple of outliers, or a lot of outliers. In that case, of course, your mean could be shifted somewhere which you don't want to have. Yeah? And for that case, a weighted mean extension could be interesting, so to say. Yeah? Yeah, that was mean shift actually.